This is Kiran Kamble, and today I'm going to cover part 2 of chapter 4. Part 1 we covered last week. So let's start. So, what is a repeated treatment design? Let's see with examples. Now, as you can see in the box, a repeated treatment design entails a pretest of the outcome O1, then administering the treatment X, then a post-test O2, then the treatment is not administered when it is supposed to be, and then a post-test number 2, that is O3, is taken. Then the treatment is administered, and the last post-test, that is O4, is taken. So it's a kind of a complex design. The attractiveness of this design is in two aspects. One is reproducibility. If you see that the treatment is repeated, so the effect is reproduced, so we can confirm whether the effect is indeed valid. Second, there are few threats to validity which can mimic this complex design of treatment introduction, withdrawal, and then reintroduction. So the most ideal outcome of this design is when O2 differs from O1 and O3 differs from O2, but in the opposite direction of O1 and O2. And the difference between O1 and O2 and O3 and O4 is similar. A classic example of this design is the experiment by Powers and Anglin in 1993, where they used methadone to counter the narcotic use addiction. This design is also very popular among researchers in psychology. Now, what are the validity threats to this in this design? So, the this design is actually strong against threats to internal validity, except in case where cyclical maturation may occur, uh, especially when the schedule of measurement is so perfectly matched that there is a confusion about which the effect of the assigning the effect to the treatment. The design may also be susceptible to external validity and statistical conclusion validity threats due to sampling errors. Lastly, construct validity could also be threatened by effect on the participant's behavior, which is typically seen as a resentful demoralization due to the withdrawals and then again admission of the treatment. So what are the suggested remedies to control these threats? One is check for environmental influences to counter threat of cyclical maturation. Larger sample sizes and appropriate statistical tests can be used to counter the threats. The participant behavior should be closely watched, and there should be adequate delay between the introduction of treatment and its reintroduction. Also, random distribution of the treatment introduction, reintroduction, and withdrawal should be undertaken, which is difficult to do, but would be the ideal situation. Uh, how can we reduce such validity threats using retrospective pretests? Now, Powers and Anglins, in their experiment of methadone for narcotic use elimination, uh, used this retrospective pretest element of the design by seeking memory-based recollection from the participants of their experiences pre-treatment, during treatment, and post-treatment. So these recollections, coupled with administrative records, can help reduce the validity threats that we discussed earlier. But what are the remaining issues in the design even after controlling for these threats? So as we've seen, the design strongly relies on a retrospective recollection of retrospective events. So there is a strong element of recollection bias, recall bias, especially when it comes to recollecting unpleasant events. Uh, there is also a threat of attrition that will remain, which is typical to any longitudinal study. And now, including an independent control group is mooted as a solution, but it's not always easy and ethical to implement. Let's move on to the next. So, what is a control group with no pretest? Designs that use a control group without any pretests are typically post-test only control group designs. And are considered in principle, very close to the classic experimental design. The use of post-test only design is typically done to eliminate the effect of testing on the study units. Such designs fall into following categories. One is post-test only design with non-equivalent groups. Second is post-test only design using an independent pre-test sample. And third is post-test only design using proxy pre-tests. So what is the classic method to support a counterfactual inference? Remember, we learned about counterfactual, the very fundamental of an experimental design in earlier chapters. It is conceptually, so what is counterfactual? Counterfactual is conceptually a hypothetical when we determine what would have happened in the absence of a treatment, which is in reality cannot be done at the same time that the treatment is occurring. So uh, typically researchers look for a similar group to support the counterfactual inference to see what would have been without the treatment. This use of a matched control group is a classic method. Let's move on to the next slide. Now, let's see what post-test only design with non-equivalent equivalent groups are with examples. So post-test only design with non-equivalent group is used when pre-tests are not available. These are non-randomly selected groups, both the treatment and the control. An example is the study by Sharp and Weatherby in 1980, where they compared infant birth weight and mortality outcomes between women receiving the women nutritional benefits from the WIC, that is the Women, Infant and Children program in the state of Mississippi. And the comparison was between these women receiving the nutritional benefits and women not receiving the nutritional benefits. Now, it is a weak kind of constitution design wise, but this test is preferred, this design is preferred when the testing effects are to be eliminated or avoided. So what are the validity threats uh, in this design? There are possible threats to internal validity. One is unknown pretest differences because there is no pretest, so unknown pretest differences between the groups due to non-random selection effects, which are difficult to decipher from the treatment effect. So we don't know the pre-treatment differences, and then it becomes very difficult to decipher the treatment effect from the effect that would have occurred due to other threats or confounding variables. Second is differential testing effects. Though rare, they may occur. So what are the suggested remedies to counter these threats to the post-test only design with non-equivalent groups? The remedies to counter these threats are: one, using variation of the test, which can be calibrated using item response theory. So we use different variations, but this should be calibrated using item response theory for validity. Using Solomon four-group design can be done. Avoiding self-reporting issues. Using bogus pipeline techniques. Using retrospective pretests. Using explicit reference groups to anchor responding. So these are the methods that typically are used to counter the threats. Now, can we counter or reduce these validity threats using independent pretest samples that we just discussed about? So when it is not plausible or possible to gather pretest data, pretest information is obtained from a randomly selected group from the same population with the post-test. So the same population where the treatment group is derived, the another sample is derived, and then their pretest data is looked at. This avoids the testing effect in the treatment population, which is a threat to internal validity. It also eliminates the threat of attrition arising when follow-up with the study participants. And random pre and post-test samples from the same population is a must to avoid any selection bias So that should be remembered. This design is recommended when there is a need for independent group, which is compelling. Uh, Special attention to sample size and sampling approach is important, although in this design. So using proxy pretest that we talked about briefly in terms of reducing the threat. So how do they reduce the validity threats? So using proxy pretest method is another way to counter the threat to post-test only design with non-equivalent groups. Such proxies are conceptually similar to the outcome variable to get a clear enough picture of a true pretest. The diagram shows A1. So in the diagram, you can see that A1 is used as a proxy to B1, and which is conceptually similar to, so A1 variable is conceptually similar to the B2 variable. Now, using matching and stratifying, how can we reduce such validity threats? Matching and stratifying are commonly used to reduce the threats of post-test only non-equivalent group design. What is matching? Matching entails grouping units with similar scores on variables of interest, while stratifying is creating strata of homogeneous units. These two methods are used specifically to counter the threat of selection bias. Let's move on to the next slide. Okay. So what are these methods of matching? We talked about two different avenues. One is the matching and one is stratifying. So what are the different methods of matching? One is exact matching. So the exact unit, as the name suggests, the units have exact scores on the variable of interest, on the matching variable. Second is caliper matching, which means that scores may not be exact but lie within a range. Third is index matching, includes selection of multiple control units above and below the treatment unit. For example, cluster group matching. Fourth is benchmark group matching, which entails selecting units that are a close match to the treatment unit on multivariate distance measure. And fifth is optimal matching, which is multiple matched controls for a treatment unit and vice versa. So what are the problems with matching? Because it seems very ideal and a wonderful approach to counter the threat, but there are some problems with matching. So what are these? Problems with matching can be based on the population. So there are three types of problems that can occur. It can be based on the population that is being matched. The problems can be with the variable of interest that is being matched. And the problem also can be with the process of matching. So what are the specific issues? So there is a possibility of selection bias. There is possibility of undermatching when some predictors of the outcome are not included in the matching. Equivalence is difficult to achieve on variables not included in the match. And matching for several reasons may produce abnormal results. Population may be matched but may not completely overlap on the variable, which can lead to regression to the mean. And there may be an error in measuring the matched variable. So the next element that we would like to discuss is propensity score matching. So what is propensity score matching? Because it is considered very useful in quasi experiments. So it is statistical technique that it attempts to eliminate the effect of a treatment or a policy by accounting for the covariates that predict receiving the treatment. So PSM attempts to reduce the bias, the selection bias, due to confounding variables and other biases due to the confounding variable that that could be found in an estimate of the treatment. So typically what we do is researchers try to see the outcome difference between the treatment group and the control group. So this is the simplistic way of doing it. But this can lead to biased results because of presence of or due to effect by confounding variables. So PSM, what it does, in other words, to explain in other words, is that propensity score matching uh, gives us the probability that a unit with certain characteristics will be assigned to a treatment group as against that to a control group. So such scores, like PSM, the propensity score matching, can be used to reduce or eliminate the selection bias by balancing covariates between the treated and the control groups. With such covariate balancing, it becomes easier to match participants with multiple characteristics. So typically any participant or any unit will have multiple characteristics, but with such propensity score matching, where covariates are balanced, multiple characteristics can be matched. This is typically mimicking a randomized trial, and that's why PSM is considered to be very useful in a quasi-experimental design. Now, using internal controls, can we reduce validity threats to a, such design? So internal controls, more often than not, are drawn from a population similar to one from which the treatment group. That's why they are called internal control, because they are drawn from the same population. So this similarity reduces the threat to internal validity due to reduced selection bias, which but it still needs consideration because the bias is one has to remember that the bias is not completely eliminated. Now, using multiple control groups, can we reduce the threats? Having multiple control groups uh, would allow for a range of hidden biases to be elicited. So when you use one control group, you can only account for certain biases, but when you use multiple controls, you can bring out a range of biases, and the direction of the biases can be known. So the treatment effect can be bracketed against these biases. So we know the range of biases, so we can separate the treatment effect accordingly and uh, classify it separately. So multiple controls can be applied in two ways. One is systematic variation controls, and second is bracketing controls. Multiple controls help by first identifying the range of the threat, which makes it much more easier to control if we know the range and how to target it. Now, using a predicted interaction, can we reduce such validity threats? So, what are predicted interactions? Predicted interactions are usually based on established substantive theories. So there is some theory on which these predicted interactions are based. So these theories typically display a very complex pathway of the treatment effect, which is implausible for any other variable or threat to explain. So it is very difficult for any other confounding variable or threat to mimic this complex pathway uh, under predicted interactions, which is based on a substantive established theory. So larger sample sizes, reliability of measurement, however, these two things are very important if we want to see the utility of predicted interactions in reducing any threat. Let's move on to the last topic in this chapter, that is case control design. So what is the case control design? So unlike the categorical differences that we saw between treatment and control groups in various other designs till now, case control design entails dividing the case into groups that have experienced the outcome. So it is after the fact. So groups that have experienced the outcome and groups that are in the control which have not experienced the outcome. This is the typical approach used in epidemiology. Uh, so retrospective data is studied and then is used to assign the cause based on the outcome to the group that has experienced the outcome. The data is studied for them and those who haven't experienced the outcome, and then the cause is typically teased out and identified with the treatment effect or the outcome effect. The outcomes are typically dichotomous in this design. That is, whether the dichotomy, there are two options: whether the effect has occurred, the outcome has occurred, or not. Well-known examples of this design are the uh, causal inferences between the causal inferences of lung cancer due to smoking or thromboembolism due to the use of birth control pills. So, what is the utility of this case control design? Case control design is typically used when it is unethical to divide the participants into treatment groups and control groups. Also, when there is a huge time lag between the cause and the effect, like lung cancer or even the thromboembolism effect that we talked about. So when such huge time gap is present, it is important to case control design helps in assigning the causal inferences. It is considered resourceful in generating hypotheses about causality, as we just talked, and these designs are logistically cheaper and risk to participants is less to minimal. So the case control design has certain methodological problems and validity threats. Let us see what these are. So there are a few methodological problems and validity threats associated with case control design. These are: one, difference. There is a difference in the scientific community on defining an outcome or its measurement. There is rarely a consensus about the entire facet of any outcome. Uh, the method to measure the outcome may be unreliable. Changes, third problem may occur is changes may occur in the measures and then definition over time. Fourth, selection approaches for the outcomes of those uh, with the effect and those without can be different because of the way these two groups present. And attrition of cases may occur because of the longitudinal aspect of such designs. Exposure to cause is usually through memory recollection because this is retrospective study. So recall bias may occur and confounding covariates are usually present. So what are the remedies to counter these threats? The textbook talks about uh, two ways in which these threats can be countered. One is matched control. Second is multiple controls when matched control is not possible. And third is general population control if the cause is not well elucidated. If we don't have enough knowledge about the cause, then general population controls is used. So these are the methods to reduce the validity threats to case control design. And that was what we had to discuss about chapter 4. Till next time, thank you.